Hi statisticians, welcome to section 8.3. We're going to continue basically the same process that we followed in sections 8.1 and 8.2 in this section, with one significant difference. Now we're talking about the binomial distribution. So you'll notice the title of this section says estimating p in the binomial distribution, whereas all of the other sections in this chapter have talked about estimating the mean, mu, the population mean. So let's start by just talking about how these two things are related. Actually, if you have your formula packet in front of you and you look at the Chapter 7 formulas, you can see on there that the mean for the p-hat distribution is actually p. And remember, p-hat is the proportion of successes over the total number of trials when we're talking about binomial trials. So when we're talking about estimating the population mean and we're talking about estimating p in this section, it's because for this particular distribution they're actually the same thing. So we are continuing estimating the population mean. Okay, so let's start with a quick warm-up. This is just going to help you to recall what we know about binomial distributions and binomial trials. Suppose that 800 students were selected at random from a student body of 20,000 and given a flu shot. All 800 students were exposed to the flu and 600 of them did not get the flu. So let P represent the probability that the flu shot will be successful for any given student, and Q be the probability that the flu shot is not successful. So just to clarify what this means, P is the probability that a student does not get the flu. Does not get the, not flu with an E, just flu. So that would mean that the flu shot was successful, right? So they get the flu shot and then they do not get the flu. So that is probability of success. And then Q would be the probability that they do get the flu. So let me make a couple of changes right on this first question. There are a few typos in this section, so I apologize for that ahead of time. Here are the first couple of them. We're going to find P hat and Q hat. And the reason we can only find P hat and not just P is that all we have is a sample. So P by itself means theoretical probability, whereas P hat means the proportion basically just that we're given in the problem. So P hat is going to be 800, let's see, 800 students were exposed to the flu and 600 of them did not get the flu. So the proportion of students who had a successful flu shot is 600 over 800, or in other words, when you throw this into your calculator, 0.75. There's the probability of success. And again, success means did not get the flu. So that tells us that Q hat, the probability that they did get the flu, has got to be 0.25. Either you didn't get the flu or you did get the flu. There's no other option, which is part of what makes this a binomial distribution. So binomial trials, remember, they only have two possible outcomes. And we call those outcomes success and failure, even though they don't necessarily correspond to something good or bad happening. But two outcomes only. So there's no third way that could have ended. You either do get the flu or you don't. Okay, part B, what is the total number of trials, N? Well, even though there were 20,000 students total, 800 of them are really in this sample. So 800 is the sample size, total number of trials. 800 students got the flu shot, right? And then what is the value of R, the number of successful trials? Well, R would be those 600 students who got the flu shot and then also didn't get the flu, even though they were exposed. Okay, last thing, Find NP and NQ and decide if this binomial experiment can be approximated by a normal distribution. So if you recall back to chapter 7, we had to have a certain condition met to be able to approximate a binomial distribution by a normal distribution, and that was that both NP and NQ must be greater than 5. So that's what we're checking for here. So let's start with NP. So NP in this case is 800 times our 0.75. We're going to assume this is our theoretical probability, so P is 0.75. 800 times 0.75, which is 600. Well, 600 is certainly greater than 5, so that first condition is met. And then again, NQ, N is 800, Q is 0.25. We're using Q and Q hat sort of interchangeably here. And 800 times 0.25 is 200, which is also certainly greater than 5. So, can this binomial experiment be approximated by a normal distribution? Yes, it can, because these criteria were both met. Okay, so again, let's come back to this idea of P hat versus P. P hat is basically when you only have a sample to look at. So like, I don't know the theoretical probability, for example, that someone is exposed to the flu and then doesn't get it after they get a flu shot. But what I do know is that when these 800 students got the flu shot, 600 of them did not get the flu. So we can sort of approximate the probability of success based on that. And this is called a point estimate. Point estimate, which is basically an estimate based on a sample, which is what we're doing with that 800. 800 is a sample, so we'll estimate the probability of success using a sample. P hat equals number of successes. R is the number of successes over N, which is the total number of trials. So P hat is basically our sample estimate of probability of success. And then just the same as Q and P have to add up to 1, same with Q hat and P hat. And again, what I'm saying here is hat. That's what that little caret thing is, it's a hat. So again, these are our point estimates for P and Q. And if you're looking at your formula sheet, this is for actually the P hat distribution. Mu sub P hat, the population mean was just P, and the population standard deviation for this particular distribution was given by the square root of PQ over N. So these are the important formulas for a binomial distribution, which is what we're dealing with in this section. Okay, so given that, we have a special formula for the error only when we're dealing with a binomial distribution. So only for a binomial distribution, the error is given by this new formula. Again, you don't have to memorize this. This is all in your Chapter 8 formula packet, although I will just point out that in your packet it's written just slightly differently. So it's written Z sub C, this is our critical value, times the square root of P hat, and then instead of putting Q hat in your formula packet, it says 1 minus P hat. But of course, 1 minus P hat, whatever's left over, that is Q hat. So there's just like a minor difference there, but they're really the same formula. Okay, so you don't have to memorize this. It's all written down for you. So again, the confidence interval then, remember it used to be x bar minus e, and then on this side, here's another one of those typos in this packet, used to be x bar plus e, but in our case, instead of the sample mean, we're using this point estimate for the probability. So basically, this is the exact same formula, but now it's adapted to the language of a binomial distribution. So all these formulas are in your formula packet, but just to point out, it's the exact same formula that we're using, except the sample mean is that estimate of the probability of success. So really the same thing, but just in slightly different language that's specific to a binomial distribution. Okay, so the same criteria do apply. In order to use this estimate for the mean, the number of trials must be sufficiently large so that both NP hat and NQ hat are larger than 5. Okay, so with that in mind, suppose, going back to this is the same example from the warm-up. Suppose that 800 students were selected at random and given a flu shot. All 800 were exposed to the flu. 600 of them did not get the flu. Let P represent the probability that the flu shot will be successful, meaning the probability that a student did not get the flu. Let Q be the probability that the flu shot was not successful, meaning they did get the flu. And find a 99% confidence interval for P. Okay, so here we are. We're going to use this formula. P hat minus E is less than P. Basically, P takes the place of mu. So in the same way that we never plugged in anything for mu, we're also never going to plug in anything for P. And then P hat plus E right here. Okay, so from the warm-up, we know that P hat is 0.75. So we already have that value. That's just from the warm-up. Remember, we just did 600 over 800 for that estimate of the probability of success. Basically, it's like our sample probability of success. And now we just need to find the error. So the formula for the error I'm getting from right here. It's also on your previous page and it's also on your formula packet. So Z sub C, the critical value, using our Z table, times P hat times Q hat under the square root all over N. Okay, so let's think first about our critical value for Z. Well, that just depends on how confident we want to be, and we want a 99% confidence interval. So going back to your 8.1 packet, remember you've got this formula, or not formula, you've got this table. I've kind of messed mine up a little bit, but you've got this table for all of your different confidence intervals and critical values. And in our case, in this example, since we want a 99% confidence interval, we want that 99% critical value, which is going to be 2.58. Notice we're back to using Z. In section 8.2, we were using T, and now we're back to using Z. And I'll talk a little bit more about that in just a few minutes, but for right now, just make a note of that. We are back to using Z. So our critical value is 2.58 just from that table, times the square root of P hat. Well, we said P hat is 0.75. Q hat is 0.25. It's whatever's left over. And then over this, over N, N is our total number of trials, and in this case, total number of trials is that 800 students. So throwing that into my calculator, I'm going to round this to 4 decimal places. It's pretty small. When I throw this all into my calculator, I get 0.0395. So there's my error. Okay, so now basically I just take this value and I take this value and I plug that right into my formula. So now I've got this, I've got this, I've got this, I've got this, and remember, P stays P, just like mu stayed mu. Okay, so writing down a final answer here, I'm going to say P hat, so 0.75, minus the error, so minus 0.0395, is less than P stays P, is less than 0.75 plus 0.0395. Really running out of room. Okay, when I add those together, subtract on this side and then add, my final answer is P is between 0.7105 and 0.7895. I'm 99% confident that the real probability, not of a sample, but of the entire population, probability of success, is somewhere between 0.7105 and 0.7895. Now, that seems like a pretty reasonable estimate because remember, for our sample of 800 students, we found a sample probability of 75%. So this is about 71 and 79% if you're rounding these things. So right in the ballpark of kind of what we already found. Okay. Now, I just want to point out here that we actually see this whole thing about confidence intervals all the time. A lot of times, especially like in election years, when you hear any results about a poll, they'll talk about a margin of error or they'll talk about a confidence interval. So in general, a lot of times we hear about a 95% confidence interval. And that just means that usually in the problem, they'll kind of give you a margin of error, and that's like based on your 95% confidence interval. So as an example, a poll of CNU students found that 23% of students have a class before 9 a.m., back when we had classes. The margin of sampling error was plus or minus 2 percentage points and was based on a 95% confidence interval. So plus or minus 2 percentage points, that's important. Find a 95% confidence interval for the percentage of students who have a class before 9 a.m. Well, the plus or minus 2 percentage points here corresponds exactly to this plus E minus E. So plus or minus is what they're talking about the error. This is telling us the error in this is 2%. And actually, the language of this problem is already in percents, so we'll just keep it like that. We won't convert anything over to a decimal. So let's keep 23% as 23%. Let's keep 2% as 2%. So basically what this is saying is that we found a sample statistic of 23%. 23% of students have a class before 9 a.m., but that could be decreased by 2% or it could be increased by 2%. Essentially, this is the P hat in our formula and this is the E. So plugging that into our confidence interval formula here, I find 23% minus 2% is less than P is less than 23% plus 2%. Or in other words, let's see, 23 minus 2, 21%. So P is between 21% and 25%. So the language of this problem is basically implying that we did not give this poll to the entire population of CNU students. We're assuming that this 23% came from a sample. And so that's why it might be a little bit off from the population probability. And so 23% came from our sample, but basically we're saying we are very confident, 95% confident, that the real answer for every single CNU student is somewhere between 21 and 25% that have a class before 9 a.m. All right, so the last thing that we'll do in this section is estimating or coming up with a sample size. So remember, at the end of section, I think it was 8.1, we talked about coming up with the sample size based on the level of confidence or based on the margin of error that you wanted. And we can do the exact same thing for a binomial distribution. So, first of all, if you have a preliminary estimate for P, then your sample size is given by P times Q times the quantity of your critical value over the error squared. If you don't have an estimate for P, so you have no idea where you're starting, then instead of this P times Q, you just use 1/4, and the rest of the formula is the same. So this is for coming up with an estimate, coming up with a sample size, basically like how many people do you need to give this survey to, or whatever it is. And again, same thing as in the previous section, if n is not a whole number, you're going to just bump this up to the next highest integer. Also, if necessary, this would be rare that this would happen, but if necessary, increase n to ensure that both NP and NQ meet those criteria for this to even make sense at all. They both have to be greater than 5. All right, so let's put that to work. A company is in the business of selling wholesale popcorn to grocery stores. A buyer for the company is examining a large amount of popcorn from a certain farmer. Before the purchase is made, the buyer wants to estimate P, the probability that a kernel will pop, right? So they don't want to buy a big bucket of popcorn and then like only a few of the kernels actually work. Suppose a random sample of n kernels is taken and r of these kernels pop. So r successes, meaning they pop, n total trials. The buyer wants to be 95% sure, there's our confidence, that the point estimate given by r over n will have an error less than 0.01. So there's our error. Okay, two questions. Two questions because we have two formulas here. First of all, if no preliminary study is made to estimate P, how large a sample should the buyer use? Okay, well, looking at our two formulas, the first one says if you do have an estimate for P, and the second one says if you do not have an estimate for P. And this is specifically saying if there is no preliminary study done to estimate P. So we are in scenario number 2. If you do not have an estimate, you have no idea where you're starting, we'll use this formula. So n equals 1/4 times the quantity, the critical value, z sub c, over the error squared. Now, I already know the error. The error is 0.01, so I'm going to put that in the formula. And so the last thing that I really need to do is figure out this critical value. And the critical value is only dependent on this confidence. So going back to my 8.1 notes, 95% confidence goes with a critical value of 1.96. So there's my z sub 0.95 in this case. All right, so what did we say, 1.96? Was that it? Yeah. And then this quantity is squared. Now, careful how you put this into your calculator. You do want to use parentheses around this part just to make sure that you are only squaring this quantity and not the entire thing. So when I throw that into my calculator, I think this one's going to come out to be a whole number. So 1.96 divided by 0.01, square that, and then multiply it all by 1/4. This one actually comes out to be a whole number as it is, so there's no need to increase this to the next highest whole number. It already is a whole number. Okay, how large a sample should the buyer use? This particular buyer should test 9,604 popcorn kernels. If you sample 9,604 popcorn kernels to see if they're going to pop, then you will have an error of less than 0.01. That's how many kernels of popcorn you need to test. Okay, so that's if we have no idea where we're starting. If you have no idea where you're starting, it's kind of like worst case scenario. So in the second example here, in the second question, we are going to have a preliminary estimate. And so you'll notice that this is a really large number. Once you have an estimate, we won't have to take as large of a sample. So the answer for number 2 is going to be a lot smaller because basically we're in a better situation here having a preliminary estimate for P. So since we have a preliminary estimate for P, now we're using this formula. So P times Q, these are going to be our estimates, times that same quantity squared. So plugging that in. N equals P times, your formula here says 1 minus P, but really that's Q. Z sub C over E squared. Okay, our preliminary estimate for P is 0.86. Well, if that's our preliminary estimate for P, then what does that make Q? Makes it 0.14. And then times, same critical value, we still want to be 95% confident, so 1.96 over the error, 0.01, and squared. Now, when I throw this into my calculator, this time you are going to get a decimal. The decimal that I find is 4,625.29. But of course, that's not a number of popcorn kernels that's realistic, right? Like I can't take 0.29 of a popcorn kernel. And because I want to be as conservative as possible, I'm always going to increase this to the next highest whole number. So my sample size is actually going to be 4,626 popcorn kernels. And again, as I said, much smaller than this first question where we had no preliminary estimate. If you don't have a preliminary estimate, your sample size is going to be pretty big. Okay, so that's the end of that section. I do want to just clarify something really quick, and then we'll start on the I really understand this problems. So the last time we talked, we made this little decision tree. So do we know sigma, the population standard deviation? And the decision tree looked like this. If you do know sigma, then you use z. So that still holds. Now this was 8.1, basically was this branch. 8.2 was no, we do not know sigma. And in that case, we use a different distribution called the student's t distribution. You use t. You do the exact same formulas, but instead of using a z, now you use a t, and instead of using sigma, you use s. Okay, so now in 8.3, we have a third scenario, which is that is your entire distribution a binomial? Are we dealing with binomial trials? In which case, you won't know anything about sigma because you'll be talking about p's and q's. So you'll definitely know if it's a binomial situation because you won't have any sigmas. You'll have p's. If it is a binomial trial, then you're going to go right back to using z. So no student's t distribution in this situation at all. The only time you use the student's t distribution is on this branch. Do we know sigma? The answer is no, then you use t. But if you do know it, or if it's a binomial distribution, you're going to use z. Okay, so pause your video at this point and try the I really understand this questions, and I'll go over them momentarily. Okay, so hopefully you've had a chance to try these, but we'll go through them. A random sample of 188 students at a large dormitory cafeteria showed that 66 of them chose the vegetarian option as their meal plan. Let P represent the proportion of students selecting the vegetarian option as their meal plan. What is a point estimate for P? Okay, so again, this is a sample. This 188 students is not the population, and P is for population, so we can't just directly from the problem say what P is. What we can say is basically our estimate, our sample estimate of P, which we call P hat. So P hat from this problem is 66 of the students over 188. And when I put that in my calculator, it actually comes out to be a pretty ugly decimal, 35106, and I'm just going to go ahead and round that to 0.35. So there's my point estimate for P. We can't say it's P because we don't have the entire population, all we have is our sample. And then just to add on to this, if P hat is 0.35, what is Q hat? So that would be 0.65. You just do 1 minus this. Okay, find a 90% confidence interval for P. So a confidence interval would look like P hat minus the error is less than P is less than P hat plus the error. I already know P hat, and P just stays P. We don't plug in anything for P, which means that all we need to do in this problem is find E, the error, and we have a formula for it. The first thing that the formula says is that we need our critical value. And this is all coming from z's, right? So we need our z critical value. And then it's going to be times the square root P hat times Q hat all over n. And we have all of these things. So let's look in the 8.1 notes and get this critical value for a 90% confidence. So going back here, here's 90% confidence, and there is our critical value, 1.645. 1.645. Okay, times the square root. Now, P hat, we already got this in part A, is 0.35. Q hat, we optionally did that in part A, is 0.65. And n, the total number of trials, well, that's our sample size. So 188. And when I put that in my calculator, I get approximately 0.06. So now plugging all of this in, everywhere I see a P hat, I'm going to say 0.35. And everywhere I see E, I'm going to put 0.06. And P stays P. Don't plug in anything for P. 0.35 plus 0.06. Now simplifying that, 0.35 minus 0.06 is 0.29 is less than P, and then what, 0.41? So P, the actual probability for the whole population, we're 90% confident, is somewhere between 29% and 41% of students will choose the vegetarian option. Okay, part C says to compute the confidence interval, we use a normal approximation. Does this seem justified? Well, what this is really asking is about that criteria that has to be met to be able to approximate a binomial distribution by a normal distribution, which is that NP and NQ both must be greater than 5. So we'll just check that. NP is 188 times 0.35, which is 188 times 0.35, 65.8. Definitely greater than 5, so that's good. And then NQ, 188 times 0.65, which is 122.2, which is also greater than 5. So definitely this does seem justified because NP and NQ are both greater than 5. Okay, problem number 2. What is the minimal sample size needed for a 99% confidence interval to have a maximum error of 0.06? And now we've got 2 add-on questions here. First of all, if a preliminary estimate for P is 0.8, and then part B, if there is no preliminary estimate for P. Okay, so we've got 2 different formulas. if you have an estimate for P, then your sample size is given by P times 1 minus P, or you can just say Q, times critical value over the error squared. If there is no preliminary estimate for P, you basically take this P times Q and replace it by just 1/4. And the sample size is going to be bigger if you don't have any starting place. So this is going to be sort of a worst case scenario compared to part A. All right, so let's start. Everywhere we see a P, we'll plug in 0.8, which would make 1 minus P 0.2. Now we need our critical value, and in this case for a 99% confidence, our critical value is 2.58. So 2.58 over the error, which we said 0.06, and this quantity is squared. So make sure that you're being careful here with your parentheses, because we don't want to accidentally square the entire quantity. So squaring this first part, just this part alone, I get 1,849. And then I'm going to go through and multiply by 0.8 and then by 0.2. And I find a decimal answer, so 295.84. Now, regardless of the way that this rounds, I mean, this one rounds up anyway, but even if it didn't, we always want to increase this to the next highest number, so my sample size here is going to be 296. 296. Now, that's going to be a smaller sample because we had a starting place. Part B wants us to do the exact same thing, but now we don't have anywhere to start for P. No preliminary estimate. So instead of that P times Q at the beginning, we just put 1/4, and then exactly the same numbers for the rest of it. So 2.58 over 0.06. This part is still squared. So plugging this in, I get 462.25. And so my question, if we were all in class right now, would be, should I round this down to 462? Because obviously if it's a 0.25, it would round down. So maybe my sample size should be 462. But of course, it's not really about rounding. It's that we always want to be on the most conservative about our sample size that we can. So even though it rounds down, I'm actually going to bump this up to a sample size of 463, which again is bigger than that 296 because you're kind of in a I don't know, a weaker spot if you don't have a preliminary estimate for P, so you need to have a larger sample to make up for that. Okay, so just to sum this all up, the 3 sections in Chapter 8 are all about estimating the mean, the population mean. Now the question then becomes, do we know the population standard deviation? And if you do, then you use Z. If you don't, you use T, the student's T distribution. And if we're not actually talking about mu or sigma, if we're actually talking about a binomial distribution, and we're talking about P's and Q's, then again you use Z. Okay, so at this point you're prepared to do all of the Chapter 8 homework and the Chapter 8 quiz, and I will see you back for section 9.1.